Today we are going to study textile industry. Our main focus of this lecture is performance evaluation of Stenter oblique dryer. In textile industry, we have processes and broadly monitor we have to monitor performance of process equipment. Some of these are performance evaluation of ring frame. Another is motor performance monitoring. Another one is performance evaluation of Stenter, or dryer, and the fourth one is performance evaluation of dyeing machine. In terms of processes, we have broadly these four processes, and today we are going to study performance evaluation of Stenter or dryer. Stenter is a very versatile equipment and it has many uses. Uses of Stenter: it is for pulling the fabric to width. It may be used in chemical finishing. It is also used for heat setting. It is used in curing and it is also used in drying. Topic of our focus here. Now something about Stenter. Stenter is a hot air dryer held in place either by clips or pins. Here fabric passes through a chain drive. Stenter has many chambers. In each chamber, air is blown through the radiator in which steam or thermic fluid is passed. We will study about thermic fluid heater while evaluating performance monitoring of utilities that are used in textile industry. The hot air is circulated above and below the fabric and is exhausted to the atmosphere by exhaust fans. Now we are going to discuss methodology, how we are going to evaluate the performance of Stenter or dryer. For this we will estimate efficiency of Stenter oblique dryer. How this will be done? For this we will have to know total moisture removal from the fabric or cloth or material or substance. First and the foremost task is to know in this process how much moisture will be removed from the fabric and energy required to drive the moisture will be we will have to find out this, and this is also known as useful energy spent in the dryer. And finally we will find out total input heat energy to dryer. Knowing these, we can find out dryer efficiency. Dryer efficiency will tell us about the performance of Stenter or dryer. Now we are going to elaborate dryer efficiency. Dryer efficiency percentage term is equal to useful energy spent in the dryer divided by total input heat energy, and we will multiply it by 100 because we are finding percentage. Now the main task here is to elaborate this useful energy spent in the dryer. This is equal to energy required to drive out the moisture. As we have seen just a few minutes ago, divided by total input heat energy. In fact, denominator term is very obvious, so we are carrying it out. Now, energy required to drive out the moisture, it is what? It is the sum of sensible heat plus latent heat of evaporation divided by total input heat energy into 100. And as we know, sensible heat is mass multiplied by specific heat capacity multiplied by temperature difference. Here mass is total moisture removed from the material, or mass of the moisture removed from the material multiplied by a specific heat capacity of water multiplied by temperature rise of the water in the material. It may be fabric or cloth. This first term is sensible heat. As we know, sensible heat is ms delta T. We have specifically written these terms to clearly define sensible heat here. And the next term is latent heat of vaporization. This will be total moisture removed from the material multiplied by latent heat of vaporization of water. These we have found latent heat of vaporization here. This whole term will be divided by total input heat energy and will be multiplied by 100. Now we can write total moisture removed from the material is m in minus m out. That is mass of moisture. M in is mass of moisture input into the process, and m out is mass of moisture, your output mass of moisture. The difference of the two will give total moisture removed from the material. This will be multiplied by a specific heat capacity of water and T out minus T in. This is the temperature difference. Thus we have written sensible heat, and m in minus m out multiplied by latent heat of vaporization of water, that gives a latent heat of vaporization. This will be divided by total input heat energy. We will multiply by it to 100. We can see here three important terms in performance evaluation methodology of a Stenter or dryer. First term is m in minus m out. That is input mass of moisture in the process and output mass of the moisture, and this is total moisture removed from the material. And the whole numerator term, it represents energy required to drive out this moisture, and the third term is total input heat energy or fuel energy input. With these three informations, we will be able to find out the efficiency of dryer. But it is very important to understand how to find out the mass of the moisture that has been removed. For that, we will find out a general formula so that we can use it in any type of problem. It will be a generalized formula. Suppose this is a process and this process is moisture removal process in dryer. Here we have P in. P in is mass of input feed material, the material that is being fed into process. Now understand here clearly the mass that is being fed into the process. It has two components. One is solid and the other is moisture. We will call it M in. M in means moisture of mass of input moisture, and this M in is suppose X percentage of P input. It is very important to understand it here that the material we are feeding in the process that has mass P in, and it is the composition of solid and moisture. So we can write input mass of the material is equal to S plus solid plus mass of moisture, or we can write P in is equal to S plus what is the value of input mass of the moisture? We have calling it X% of P input, or we can write P input is equal to S plus X% means 0.01 X into P in, rearranging, taking common P in 1 minus 0.01 X is equal to S. This is a very important derivation for us. It will help us in finding S, or if need be, we can, given any two, we can find the third one. So here its significance is that we will be able to find out information very easily. Now after process, we have P out. P out is the mass of output product material, fabric, cloth, and again P output will have two components. One will be solid and the other will be moisture. Here moisture is mass of M out, mass of output moisture, and let us call M out is equal to Y percentage of P out. What is important to see here, that the whole process is about the removal of moisture. So the percentage of only moisture will change and the solid will remain the same. Okay, only in the process percentage of moisture will change, solid will remain same. So we can write here P out is equal to S plus Y percentage of P out, means P out is equal to S plus M out, or P out is equal to S plus 0.01 Y into P out. Rearranging P out 1 minus 0.01 Y is equal to S. This is again very important relation for us. We can use, if we have found S from input side, this S can be used in output side because this S solid does not vary. So we can find out P out here, and using P out, if we have been given percentage of output moisture, we will be able to find out M out, mass of moisture that is getting out. So we will be able to use M in and M out using this approach. So this is a generalized approach through which we will be able to find out M in and M out. M in is nothing but 0.01 x into PIN, and M out is nothing but 0.01 y into P out. This is a very important derivation, and in any sort of problem, whether simple or complex, we will follow this approach and we will be able to find out the answer. So thus we have find one thing that is useful in the case of finding dryer efficiency. Another information that we know specific heat capacity of water is equal to 4.18 kilojoule per kg degree centigrade, and in terms of kilocalorie it is 1 kilocalorie per kg per degree centigrade, and latent heat of vaporization of water, this is equal to 2260 kilojoule per kg at 100 degree centigrade, and in terms of kilocalorie it comes out to be 540 kilocalorie per kg. With this information we can solve an illustrative problem. Now we will solve an example so that we can appreciate what we have learned so far. This is the example. The question says the throughput of a textile stenter is 1000 kg per hour. The inlet moisture content of the cloth is 50% and the outlet moisture is 5%. The inlet and outlet temperature of the cloth is 28 degree centigrade and 80 degree centigrade. The stenter is supplied with steam at an enthalpy of 660 kilocalorie per kg. The condensate leaves at 90 degree centigrade. The flow rate of steam is 1000 kilogram per hour. Estimate the overall thermal efficiency of the dryer. The latent heat of vaporization of water is 540 kilocalorie per kg. We have to solve this problem. First of all, we will see moisture removal in the process. This is the process, moisture removal process in dryer. Here we have P in, mass of feed material that is going inside process, and this has been given as 1000 kg per hour. The moisture content of the cloth is 50%, means X is here 50% and the outlet temperature is 5%, means Y is equal to 5%. P out we don't know. Using this formula just we have derived now, P in 1 minus 0.01 x is equal to S. We have the formula, or we have been given 1000 P in 1000 kg per hour, 1 minus 0.01, value of x is 50, or we can, using this, we will get S is equal to 500 kg per hour, and mass of input moisture M in is equal to X percentage of P in. So this comes out to be 0.01 into 50 into 1000 kg per hour. This will come out to be 500 kg per hour. So we have mass of solid also, and we have already find out M in. Now we have to find M out. For that we have formula P out 1 minus 0.01 y is equal to S. Here we don't know the value of P out, so 0.01, and y is 5% here, and from the data given of P input we have found out S is equal to 500 kg per hour, because S does not change in the process, so it will remain same before input and after output. So P out is equal to 500 divided by 1 minus 0.05. This comes out to be 526.32 kg per hour. Once we know P output, then we can find out mass of the output moisture. M out is equal to Y percentage of P out. This will be equal to 0.01 into Y into P output 526.32 kg per hour, and after multiplication we will get the value 26.32 kg per hour. So we have M in and M out. So we can find out the mass of moisture that has been removed. M in minus M out. This is equal to 500 kg per hour minus 26.32 kg per hour, and this comes out to be 473.68 kg per hour. What is this? This is the moisture removed. This is the mass of moisture removed using this process. Once we find out moisture removed, then it is very easy to find efficiency using the formula in numerator and denominator. In numerator we use useful energy spent in dryer. It had two components, sensible heat and latent heat. Sensible heat here, mass of moisture removed 473.68 kg per hour into specific heat capacity of water in kilocalorie term. It will be 1 kilocalorie per kg per degree centigrade, and temperature difference in the question. Temperature difference has been given as output temperature is 80 and input temperature is 28. Thus, we have written the first term of sensible heat and the second term, that is of latent heat of vaporization, moisture removed, mass of the moisture removed, this kg per hour, and we have latent heat of vaporization given as 540 kilocalorie per kg. We will calculation 24,631 kilocalorie per hour, because this kg, and this is in degree centigrade. This will be off and we will left with kilocalorie per hour plus 255,787 kilocalorie per hour, and the total sum will be 280,418 kilocalorie per hour. This is the useful energy spent in dryer. You may ask one thing here, 540 kilocalorie per kg is the latent heat of vaporization at 100 degree centigrade, and here we have output only 80 degree centigrade. For your information, I will tell you that the vaporization takes place at every temperature. That is why in winter, if you keep your cloth for drying even in room, after certain time it gets dried and you can use it. It so happens that when the temperature is less, latent heat of vaporization for water will be more, and if you use steam table, you will find that latent heat of vaporization at 80 degree centigrade is nearly 555 kilocalorie per kg. So for simplification, we are using 540 kilocalorie per kg, and this information is given in the question also, that you have to take 540 kilocalorie per kg for latent heat of vaporization. Now we have to find total heat energy input to the dryer. For this, we have two information given here. It is given here that steam that is supplied to a Stenter has enthalpy of 660 kilocalorie per kg, and after process it comes out at 90 degree centigrade, and somewhere there will be tank where this condensate will be collected, and suppose this is boiler and steam will be, thus this cycle will get complete. Total energy input to the dryer will be 660 kilocalorie per kg minus 90 kilocalorie per kg. Condensate is at 90 degree centigrade, and at 90 degree centigrade, if you will see the steam table, you will find that the enthalpy is 90 kilocalorie per kg. So total energy input to the dryer is the difference of these two. I hope you will appreciate this point. So, and It is also given in the question that flow rate of steam is 1000 kg per hour. So we find total heat energy input to the dryer. This comes out to be 5,70,000 kilocalorie per hour. Okay. So here this portion in process is related to steam that is being supplied to the Stenter or dryer, and this side we are providing feed material, and after process we are getting output product. So this is the brief representation of both the system. Now we can find out dryer efficiency very easily. We have already found out useful energy spent in dryer, that is 280 418 kilocalorie per hour, and heat input we have find out to be 5,70,000 kilocalorie per hour, and for percentage we will multiply by 100, and this comes out to be 49%. So here we have found out the efficiency of the dryer. After knowing these things, it is important to understand now what are the opportunities to reduce energy consumption in Stenter dryer. First way could be reduce the evaporation load. What is evaporation load? Mass of input moisture, reduce it. Second method may be increase the dryer efficiency. We have just find out for this case dryer efficiency has come out to be 50%. How we can improve dryer efficiency? We can use improved insulation, reducing heat losses, or installing heat recovery. Third way would be improve the energy supply system. Means increase boiler efficiency, or use alternative low cost fuel. So using these three methods, we have opportunities to reduce energy consumption. In the next class, we will study performance evaluation of dyeing machine. You were watching Fazari energy audit classes. Okay, thanks for watching.